Hi everyone, we're just going to carry on with our 6.3 notes here. So we're just starting where I left off. Okay, we were looking at the first example and we decided that we had we picked two possible solutions to our graph. So going back here for a moment, we just picked 2 points that were in the solution set. And if I wanted to verify that one of those points was indeed a solution, in other words, I want to make sure that I graphed it correctly and that I am picking a correct solution, just like I did with a system of equations, I can take that point. So for example, let's choose this point right here. Let's check 4, 1. And I can substitute it into both of my linear equations. I want to make sure that it checks out, or it's valid, it's true for both of my linear equations. So what I'm going to do is I'm going to substitute, or I'm going to verify. Let's verify the point 4, 1. So I'm going to substitute this point into both linear inequalities. So we can go back to our linear inequalities that we had there. Okay, so we can, here's our first one that we had, y is greater than -3/2x minus 3. Okay, the other linear inequality I had is y is less than or equal to 3. Okay, so this time I'm just going to take this point. Remember that x is 4 and y is 1. And I'm just going to plug those values in for y and for x into both of them. So I'm going to put a 1 in here for the y. Okay, so it's 1 is greater than -3/2. And instead of x, I'm going to write 4 for x. Okay, minus 3. Okay, we could go ahead and solve that now. Okay, so let's simplify this. On my left-hand side, I have 1 is greater than. I could do the math here. -3 times 4 is going to give me a -12 on the top, still over 2. Okay, minus 3, and I can simplify that even more. 12 divided by 2 is 6, so I have -6 minus 3, and then I've got -6 minus 3. Well, that's going to give me a bigger negative, -9. Okay, so the statement 1 is greater than -9, that's true. 1 is a bigger number, greater number than a negative number. So that's a true statement. Okay, it's valid. Let's come over to the other linear inequality and do the same thing. I'm going to substitute in the y value for my point, which was 1, in for that y. Okay, so you leave the formula for your linear equation all the same. You're just going to put in the values of your point and substitute them in. So I've got 1 is less than or equal to 3. Well, 1's not equal to 3, but it's true to say that 1 is less than 3, and so that's true. Okay. So I have verified the point 4, 1, and I can say that 4, 1 is a valid solution. So yes, the point 4, 1 is a valid solution. Or another way to say that is, it is in the solution set. Great. You don't always have to verify your point unless you're asked to. But a time when you might want to verify your point is if you were unsure if you graphed it correctly. Okay, if you were not sure if your overlapping region was correct, you could pick a point from it and just plug that point into both your linear inequalities. It should check out, or it should be valid for each of them. Okay. By the way, if it was valid for one and not the other, then it would be not a valid solution. In other words, if I picked that point from my graph and it didn't fit both of my equations, that's telling me that I haven't graphed it correctly. Okay, so it does have to be true for both of them to be a valid point. Okay, example 2, I just want us to have a little bit of, we're not going to graph these, but let's just look at the information that we're given in the problem, and we can already determine not what our graph is going to look like, but we can determine whether we have solid lines, dashed lines, and whether the point of intersection would be included in the solution region. Okay, remember, whenever I have a dashed line, okay, so anytime you have a dashed line, okay, the point of intersection between that dashed line and any other line, okay, with another line. So the point of intersection with another line, okay, will not be included in the solution set. So when I graph that, that would look like I put an open data circle at the point of intersection if I ever have a dashed line. So it looks a little bit like this if you had a dashed line, okay, and it was intersecting any other line, solid or dashed, okay, you would actually draw that with an open circle in between. So it would look like this. Okay, it would have an open circle where they intersect. So let's go ahead and look at these next questions. And for each one of them, we're going to say whether the boundaries, in other words, the boundary lines, okay, will be included, and whether the points of intersection will be included in the solution set or the solution region. So what can I tell about the first one without even graphing it? Well, okay, if I look at this first one, it says that the points x and y, okay, for this linear inequality, y is greater than or equal to negative 2x plus 1, where x and y are all real numbers. Okay, that real numbers is important to me. It tells me that when I graph this, okay, this is going to be a solid line. It's solid because of that equal sign and because we have real numbers. Okay, let's have a look at the next one. Okay, the other linear inequality that I'm going to graph is given to me right here. Okay, negative 2 is less than 2x minus y. Now, I could rearrange that. There's nothing wrong with that. Okay, if I was going to graph it, I'd absolutely want to rearrange this. However, if all I'm being asked for right now is whether I'm going to use a solid line or a dashed line, then I can just go ahead and look at the inequality sign because I can already tell, okay, that this is a strict inequality. So I'm going to use a dashed line. Okay, these are also real numbers, and I use a dashed line anytime I have a strict inequality, whether it's real numbers or whole numbers or integers, doesn't matter. Inequality signs without the equal sign, always use a dashed line. So this graph, even though I haven't gone ahead and graphed the system, I know I'm going to have a dashed line and a solid line. Okay, so I can say that the solid line, okay, the boundary so this boundary line is included. So the boundary line y equals negative 2x plus 1 is included. Okay, as well as it's whatever the overlapping shaded region will be. And here I can say that this boundary line will not be included. Okay, so I can say but the line, okay, and in this case we can say negative 2 equals 2x minus y is not included. Because one of these lines is dashed, the point of intersection will not be included either. Okay, so the point of intersection is not included in the solution set. Excellent. Let's do another one down here. It's a little bit different. Okay, I see this time I have a linear inequality. Y is greater than or equal to 3x minus 4. And here I'm told that x is a member of the integers and y is a member of the integers. So these are integers. Okay, if I were to go ahead and graph that, this is discrete. So if I were graphing this, I'd be using data points, okay, to stipple my plane as well as to stipple the line as well, okay? Again, you look at that inequality sign, it tells you what your boundary line is going to look like. It's not going to be a solid line because they're integers, okay? But it's not going to be a dashed line because it's not a strict inequality. This is going to be a stippled line. In other words, I'm going to use data points. This will be a stippled line. So that's going to be a line that's made out of data points. Okay. Down below, I've got another inequality here. And here's my inequality here. I recognize that it's 2y is less than or equal to x. And again, I have integers again. Okay. So discrete data. This will be a discrete solution set. And looking at my inequality, again, I see that it's going to be a stippled line. Well, stippled lines are just like solid lines. Every data point on that line is included in the solution. And so the only time that something is not going to be included on the boundary line is if that boundary line is dashed. So when I go ahead and describe whether these lines are going to be included in the solution set, I will say, okay, both boundary lines will be included, but I'm going to say it like this. I'm going to say the integer coordinates. So in other words, the data points that are integers. Okay, so the integer coordinates of both boundary lines are included. Okay, and the point of intersection will be included too. Okay. Assuming that these lines intersect. Okay, is included in the solution set. So we don't even have to graph them to be able to describe the solution sets a little bit. The only thing I'm not sure about here, because I haven't graphed it yet, is whether the solution region will be above or below those boundary lines. I'd have to graph it to, or at least rearrange these equations to figure out that part of it. Okay. Excellent. I'm going to pause it here, folks, and then I'm going to do one last video, a really short one, where we're going to work through an example of graphing something like this, okay, where you have discrete data and you have to use data points. So I'll get you to join me again in one last video.